Welcome back, everybody, to the next chapter in the epic saga of trigonometry. We're going to talk about the Pythagorean Theorem today. Now, this is good because now we're starting to really talk about true trigonometry. Trigonometry, generally speaking, now this is not true in all cases, but generally speaking, is going to be working with right triangles. The Pythagorean Theorem is specifically based on right triangles, so this is a very good section for us to incorporate Pythagorean Theorem into. This is not the only time that you will see it. Pythagorean Theorem is useful in all subjects of the world. Not all subjects of the world, but in a lot of cases. It's used a lot in physics, it's used in geography, it's used all over the place. It truly is a useful tool. It has been known across so many different cultures throughout history, and it has been used in so many cultures throughout history. It's most likely the most widespread theorem of probably all mathematics. I could be wrong about that. You can check it up on the internet. I'm sure you'll find something along those lines. Anyways, let's see what the Pythagorean theorem is. It says, in a right triangle, giving away about that little square, the square of the hypotenuse is equal to the sum of the square of its legs. Well, here we go. Let's try to figure out what that means. First of all, we got this word hypotenuse. If we're not sure of hypotenuse, you might want to check out the vocabulary section of the website. The hypotenuse is the longest side of a right triangle. It's also the side that's opposite the right angle. So here we go. If I'm starting at the right angle and I point towards the opposite side, it's going to hit this side, which is also our longest. So let's label that thing right here as hypotenuse. Okay, and it says that it's equal to the sum of the square of its legs. Legs would be the other two sides. We refer to each of these sides as a leg. Now, traditionally, we label these sides. We'll label one of the legs as A. We'll label the other leg as B. It does not matter which one's which. That is 100% the truth. This could have been B, this could have been A. It does not matter, the legs, which one's which. However, a hypotenuse will always be known as the C side. Okay, now this is important because when we write down the Pythagorean theorem, what a lot of people remember throughout their lives is this little thing that we call A squared plus B squared equals C squared. Now, I like to think of it as this. This makes a lot more sense to me because I'm not trying to remember plugging things in. I want to remember that the square of the longest side is equal to the sum of the two legs squared. So either way you remember it is fine, but this is the formula. And it's key that we make sure that that hypotenuse stands on its own. So let's take a look at a couple of problems and see how they work. You're going to find that Pythagorean theorem is also one of the easiest theorems to use. That's why it's been lasting for so long. It lasted its way through the Mayan culture, through the ancient Chinese culture, and through the Greek culture. It's lasted those thousands of years because of the simplicity in its use. Okay, so here's a first example. We have a square right triangle. We have a leg of 3, a leg of 4, and we're trying to find, I should have probably put the x in there, trying to find this last side. Well, this is my A side, it's 3. We're going to square it. Plus our other leg, our B side, which is 4, we're going to square it. And it's going to be equal to our hypotenuse, our C side, which is x. So let's square it. 3 squared is 9, plus 4 squared, which is 16. Still equals x squared. 9 plus 16 is 25. Now we have to think about how to get rid of this square. Well, if you remember from radicals, squares and square roots are inverses of each other. They're the opposites. So if I want to get rid of the square, I'm going to take the square root. But what I do to one side, I must do to the other. My x comes out as just plain old x. And the square root of 25 leaves me with 5. So we notice that we have a perfect 3, 4, and 5 for our solution. Whenever we have three whole numbers that work in the Pythagorean theorem, we call those Pythagorean triplets. Okay, there's an infinite number of Pythagorean triplets, but that is a different discussion for another day. Kind of a cool topic to talk about. But anyways, here's an example for you to try on your own. Take a second to pause it and see if you can come up with the correct solution for x. Alright, let's see how you did. Hopefully you recognize that 12 and 5 are our legs, so you should have 12 squared plus 5 squared equaling our hypotenuse of x squared. 12 squared is 144, 5 squared is 25. 144 plus 25 gives us 169, which equals x squared. I want to take the root of both sides. That eliminates the square on my x, and the square root of 169 is 13. Hopefully you came up with 13 as the answer too. Let's take a look at a couple of different problems. Now we should notice that we have one of the legs as our variable. Well, we can deal with that because we're still going to use the Pythagorean theorem the same way we did before. We just want to make sure that we keep our hypotenuse as the c value off to its own side. So for right now, what I have is 6 squared, one leg, plus x squared, which is our second leg, should equal 10 squared. 36 plus x squared equals 100 when I do all that work out. I need to get my x by itself, so the first thing I got to do is subtract that 36. That's going to leave me with x squared equaling 64. Now I'm pretty close to being done here. All I got to do is get rid of that square. So I'm going to take the root of both sides. That leaves me with x and equaling the root of 64, which is 8. So we have our solution here of 8. So I have one more for you to try on your own. See how you do. Pause the video and get back to me in a moment. Alright, let's check it out. Hopefully you set this up properly. When I square 8, I'm going to come up with 64. When I square 12, I'm going to come up with 144. I'm going to subtract 64 from both sides. I end up with x squared equaling 80, and I have to take the square root of both sides. Now, if you got to here, that's cool, but we should be able to simplify. We did this before. So what I'm going to look for are two numbers that are going to multiply to 80, one of them being a perfect square. Well, let's see. What two numbers multiply to 80, one being a perfect square? I'm thinking 16 times 5. 16 times 5 gives me 80. 16 is my perfect square, so the root should come out, and that 5 is going to stay in. Hopefully you got that. If you didn't, if you got to here, that's fine, but we do need to make sure that we reduce or simplify. Alright. Now, we're not always going to have the prettiest looking numbers to work with. Sometimes we're going to see things that look like this. And we got to know how to deal with things that look like this. Well, remember what we're doing. We're squaring a number. And what does squaring really mean? It means that we're taking the number and we're multiplying it by itself that many times, right? This thing times itself twice. Well, the stuff on the outside, they multiply like normal. So we're going to have 2 times 2. No problems there. And we're going to have the stuff on the inside multiply like normal. Gives me 3 times 3. Okay, let's deal with this stuff. 2 times 2 gives me 4 times the square root of 3 squared. Ah, that square thing is good. because it eliminates my radical, and I'm left with 4 times 3. 4 times 3 is 12. So we can deal with those things now. All we have to do is just write it out real quick. Okay? Some of you may recognize a pattern that will develop. Some of you may realize that we're going to end up squaring the first number and then multiplying by whatever our radicand is. So 2 squared would give me 4 times 3 give me 12. So if you recognize a shortcut and you don't need to write these steps out, go for it. But if you need to practice it for a little bit first, it's not difficult to do. So let's look at an example. Here we have our hypotenuse as 6 root 2. So these are my legs. I have 6 squared plus x squared equals 6 root 2 squared. It's going to give me 36 plus x squared equals, again, I might need a little bit of practice on this. I know I'm going to have 6 times 6 times 2 times 2, which gives me that root 2. That's going to eliminate. That's going to give me 36 times 2, which is 72. So now I have the correct number in place. I'm going to subtract 36 from both sides. X squared equals 36. Take the square root of both sides. Gives me x equaling 6. Hey, quick question. If I have a 6 here and a 6 here, what type of triangle does that make this? If you said isosceles, you're correct. Anyways, here's another problem for you to try. Give it a shot. Make sure that you put the right numbers in the right place in your Pythagorean Theorem formula. Pause the video, see how you do. Alright, let's check it out. I know that I need to have 4 squared plus 4 root 3 squared, and that must equal x squared. 16 plus, well, that's going to give me 16 times 3 because I'm squaring 4 and I'm going to square the root of 3. That's going to equal x squared. 16 plus, let's see, what is 16 squared? 32, how about 48? And if I add 16 and 48, that's going to give me 64. All I have to do is take the root of both sides, and I get x equaling 8. I have one more for you to try. Try it on your own again. Pause the video. Take a try at it, and then resume when you're ready to check. Okay, let's see. Sorry, I forgot the little square there. But here we go. I have x squared plus 6 squared is going to equal 3 root 5 squared. I get x squared plus 36. If I multiply, 3 squared will give me 9. Root 5 squared will give me times 5. Alright, easy enough to do. 9 times 5 is just 45. If I subtract 36 from both sides, that gives me x squared equaling, oh, that's just 9. And if I take the root of both sides, that leaves me with x equals 3. So my solution should be just plain old 3. Hopefully you guys got that without too much difficulty. Again, it's possible for us to have to reduce some radicals at any given point in time, whether it's during the problem or maybe we get a radical as a solution we got to simplify. Shouldn't be a problem. We should be able to handle that at this point. Any questions you have, leave on the website or bring them into class and we'll discuss them as soon as we can.